Assalamualaikum students. Today we will study about the analysis and design of welded connection in steel structures. In the last class, I have discussed about the types of welded connections and the processes that we followed in different processes that we follow in welding the connections in steel structures. And today our focus will be more towards the analysis and design of welded connections, which is basically the numerical part and the practical aspect of the steel structures. Well, before moving ahead, let's have a quick recap of the what we have studied in the last lecture and to proceed our today's lecture ahead. And so in the last class I have told you that whenever we weld a connection, there is always a root where the our weld has been initiated, and the size of the weld is called as the size of the leg. Leg is basically the length of the weld or the width of the weld that you use to join the different parts of the steel structures with each other. And then we have a shear plane, which is basically the outermost boundary of the weld, and that is called as the shear plane, whichever direction it is. It could be in xy plane, it could be yz plane, or it could be zx plane. So whichever weld we carried out our welding, it is called as the shear plane. And then we know told you about the throat of the weld, and throat of the weld is basically the diagonal distance from root till the end of the weld. So it is basically the weld is generally in the form of triangular shape. So we find out the throat in respect of the cos theta and sine theta, which is basically the trigonometric function for triangular functions. And ultimately, we know that the throat is comes out to be W into cos of 45 degree, because this plane is generally initiated at an angle of 45 degrees. So it ultimately becomes the size thickness of the throat, which comes out to be 0.707 W. And then we have to use electrodes to weld the different steel connections, and which should be matched with the base metal of the material with which our assembles are produced or our structures are composed of. And we use E70 electrodes where we have a yield stress of less than 60 ksi, and similarly we use E80 ksi when we have a yield stress of more than 60 ksi to about 65 ksi, while E60 and E40 electrodes are also used as well with the slightly lower yield stress. The nominal load carrying capacity of the weld, which is Rn, becomes equal to force or the load applied on the weld times the area of the weld. So it is a basic formula that we used for the calculation of the nominal load, which is basically equals to strength in terms of the area of the weld. And the force on the welds then becomes as 0.707 W into L. That is basically this area 0.707 L into length of the weld, whichever length of the weld that you continue for its welding in the other directions. So in multiplied with the FW, which is basically the force on the weld, and the area of the weld is 0.707 W times L. Therefore, if we find out its design strength of the weld, calculate design strength of the weld, it becomes as the phi Rn, and where phi is the factor of the safety, and its value in case of welded connections is 0.75, which is basically the same which is used for the shear design of the structure. As I told you that the strength of the weld is dependent on the shear plane, and the phi value of the factor of safety that is used for shear structures is 0.75. So that's why it ultimately becomes as 0.75 times 0.707 WL into FW. And the strength of the weld or the nominal strength of the weld per unit area is taken as zero point 0.6 times the strength of the electrode or zero point 0.6 times the force of the electrode. It is equal to zero point 0.6 Fw is equal to zero point 0.6 times Fex when the weld is connection in one direction, that is either in the horizontal direction or it is in the vertical directions. That is either it is along the x-axis only or it is along the y-axis only. Whenever we carried out a weld at an angle to at an any particular angle towards the longitudinal axis or with respect to the perpendicular axis. Its formula becomes as Fw is equal to zero point zero 0.06 times Fex force on electrode multiplied by 1 plus zero point zero point 0.5 sine of raised to power 1.5 times theta. So this additional factor of safety in the bracket is used when we have carried out a welding at an angle, at any angle in the shear plane. So these are the basics two or three formulas that we are going to use to calculate the nominal design strength of the weld. First, we should draw the value of the nominal load capacity of the R, and then we will multiply it with the factor of safety. And in order to find the value of this force Fw, that is the nominal strength of the weld per unit area, we will use either formula of zero point 0.6 Fexx or zero point 0.6 Fex into 1 plus 1 plus zero point 0.5 sine of 1.5 theta. Well, in during the drawings of the steel structures, how we would know that we will represent the welded connections, and there are many terminologies that we used to represent such symbols. For example, here if we have electrode is 70, it is mentioned at the start of the before the start of the symbol or at the tail of the row or tail of the arrow. And whether we have an electrode uses E60, E70 or E80, the electrode is mentioned before, followed by the a triangle, either on the upside of the arrow, on the downside of the arrow, or on both sides of the arrows. So if we have a triangle of the weld downside of the arrow, it means the welding is carried out towards the near side or towards the bottom side of the weld. And if it is outside of the weld, it means that the welding is carried out on the other side or the far side of the weld. Or I would say it is carried out towards the bottom of or the top of the weld. If it is on both sides, it indicates that the welding is carried out on both sides of the member. That is, the member is welded from the top as well, and member is welded from the bottom as well. While if you see any circle in the drawing, it indicates that the welding is carried out all around. It means that the member is welded from all four places or all three sides from whichever the member is connected. So if we have a member something like this, it means that it is welded from all sides of this structure. So it is welding is carried out from every part. It means this is what does this circle mean? That welding is carried out all around. And if you see a dark arrow over this circle, it means that it is carried out of field weld has been performed. Field weld means that field welding is carried out on site, particularly instead of the member of assembly at the uh, in the factory. Now, if you see some of the numbers over the triangular regions, like here it is shown as 1 by 4 and the 7. 1 by 4 indicates the thickness of the weld, that the weld is about 1 by 4 inch thick. And the next number that is on the perpendicular side of the weld, it indicates the length of the weld, and which indicates that it is of length of 7 inches, like here in this case. So thickness is mentioned on the base of the triangle, and on the towards the hypotenuse of the triangle, it is mentioned as the length of the weld. Now let's have a quick 2 to 3 examples to understand the design of the welded connections. For example, for the first figure, we are given with the three different figures A, B, and C, and we are required to find the strength of the weld. It is basically the type of the question in which we have carried out the analysis part. That we might be given that we have a weld and then we have a force, and whether our weld can sustain that particular force or not. And for that process, we carried out the analysis part of the weld. Analysis part of the weld is the first step in the design of the welded connections. For example, if we have in figure A, we see it states that it is a 3 by 4 inch weld. The length of the weld is 8 inches and welded along the weld. Alright, loaded along the weld. The force is applied along the weld. And the force is applied in the same direction in which the direction of the weld. In the second part B, it states that it is again 3 by 4 inches weld. Again, it is 8 inches long, but the force or the load is applied in perpendicular to the weld. That the force is applied in x direction while welding is carried out in y direction. In the third figure, we have again 3 by 4 inch weld, 8 inches long, but in this case, the loading is applied at an angle of 45 degrees to the weld. So we have three cases: one in the horizontal direction, in which the force is applied along the weld; second is in weld is carried out in the vertical direction, in which the loading is applied perpendicular to the weld; and in third, we have a welding which is at the plane at an angle of 45 degrees to the weld. Well, to calculate the nominal strength of the part A, we will use the formula that we have studied in the last slide, that is phi Rn is equal to phi Fw into Aw. And we studied that the value of area of the weld, or Aw, is 0.707 W times L, where W is the thickness of the weld, L is the length of the weld, multiplied by the Fw, and the value that profile that we used for welded connections is 0.75. We just need to plug in the values in here and find out the value of the strength of the weld for part A. So it will become as phi Rn is equal to 0.75, which is the value of the phi, multiplied by 0.707, the constant factor in the equations, multiplied by the W, which is the thickness of the weld, which is 3 by 4 inches, multiplied by the L, which is the length of the weld, and its value is 8 inches, times Fw. And Fw, I have told you that we have two formulas for this particular problem. And when we have a nominal strength of weld per unit area, its formula is zero point 0.6 times strength of the electrode. So it will become as zero point 0.6 times, and its weld strength well is 70, because it is the E70 electrode which has been used. So it will become as zero point 0.6 times F70. So once we simplify this equation, we will find out that its value comes out to be 133.62 kips. So we will say that for part A, the design strength of the weld is 133.62 kips. If we applied a force or applied a load less than this value, it will not fail. But if we applied a value of more than 133.62 kips, the weld is going to fail in shear. Similarly, we will move to the second part, and for the second part, we will use the same formula for area of the weld. While for calculating the force on the weld, we will use the second formula, because this formula, because in this case the force is applied at perpendicular to the weld or at an angle to the weld. An angle in this case towards the weld is taken as 90 degree because it is applied exactly perpendicular to the weld. And whenever we have a force which is applied perpendicular to the length, we will use the second formula, which is zero point 0.6 times Fex into 1 plus zero point 0.5 sine raised to power 1.5 times theta. So it will become as 0.66 into Fbxx into 1 plus zero point 0.5 sine raised to power 1.5 into theta. And theta in this case is 90 degree and sine 90 is equal to 1. So it will become as 1 plus zero point 0.5 multiplied by 1. So it will come as 1 plus zero point 0.5 and it will total becomes as 1.5. So when we multiply this value of zero point 0.6 into 70 into 1.5, we will find out that multiplied with the area of the weld, it will ultimately comes out to be 200.4 kips. Or in order to further simplify equations, we have find out the value of this weld 0.6 times Fex into phi of 0.707 W of L as 133.62. We just have to multiply this extra factor 1.5, which is basically due to the perpendicularity of the load applied to the weld, and we find out its value is 200.4 kips. Similarly, we will follow the same steps for the third part or the part C of the problem, except that in which the angle used will be of 45 degrees. That we use the value of sine theta as 45 degree, and when we take out its power raised to power 1.5 and multiply it with zero point 0.5 and add 1 to the answer, it comes out to be 1.292. So when we multiplied it with the area of the weld and the force of the weld, it comes out to be 172.7 kips. So for part C, the length of the weld or the strength of the weld comes out to be 172.7 kips. So what you would infer from this problem is that whenever a force is applied parallel to the weld or along the weld, its shear strength will be low, while whenever the force or the load is applied perpendicular to the weld, its shearing capacity will be high. So it can sustain a more load in shear whenever the load is applied perpendicular to the weld. Why this has happened? Because you have studied and you might know that the arrangement of the molecules in steel structures or in the metallic forms is in the form of the layers, where the one molecule or particular layer is arranged in one direction, and similarly the second layer is also arranged on below that layer. And when the force is applied in the same direction in which the molecules are arranged, they will be displaced easily in as compared to the force when its force is applied perpendicular. So therefore, when the force is applied in the same direction in which the metallic layer is formed, it's, it will deform or it will move from its place quickly, or I would say that it will shear quickly because there it will be complete movement of one complete layer of ion of molecules. That's why we have a lower shearing capacity when the weld is applied along the weld, when the load is applied along the weld. After this analysis part, let's move or skip to the second problem, where we have a little complex problem, which we are given with a steel section, and the steel section shape is C section. We have a weld in C section shape, like here it is shown in dark black lines, and they used E70 electrodes with a thickness of 3 by 16 inches. and the length of the member or the width of the member is given as 8 inches with the thickness of the plate half inches, that is zero point 0.5 inches, and the steel they used is A36 steel, while for the gusset plate that they used for the connection is 3 by 4 inches of the thickness, and the steel again it is composed of is of A36 steel, while the force is applied to pull the section C in which the net welding has been carried. And they used E70 electrode as I had told you in the last problem that how they represent the symbols, and 3 by 16 inches indicates that the thickness of the weld is 3 by 16 inches. Now, moreover, the length of the weld in the direction of the applied load is given as 10 inches, and the perpendicular direction it is given as 8 inches. So ultimately we can say that we have a three welds, one, two, and three. One having a length of 10 inches, second having a length of 8 inches, and third again having a length of 10 inches. So we will have two welds of 10 inches and one weld of 8 inches. Moreover, if we see that consider the weld of 10 inches, it is basically welded along the length of the weld. While if we see the weld having length of 8 inches, it is welded along the load applied perpendicular to the weld because the direction of the load is shown here. So, for in order to solve these problems, we will find out the strength of each weld separately. That we will find out the strength of 10-inch weld separately, 8-inch, then and followed by again 10 inches weld. In this case, as we have a same thickness of the weld and the same length of the weld, that is 10 inches, we can find out the value of the strength of the any one weld and multiply it with 2 to get the net results. And but we have to find out this weld number 2 which is of 8 inches. So let's see how we will proceed. So first of all, let's consider 3 by 16 inches two welds having length of 10 inches long that are welded along the weld. See the direction of the weld and the load applied of the weld is basically along the weld, which is basically the problem A in the last example. So what we will find out, we will apply the formula its equation that will come out to be 0.707 into 3 by 16 inches thickness of the weld into length of the weld. And the length of the weld for this time it will become as 2 into 10 because we have two welds of 10 inches multiplied with b zero point 0.6 into 70 because we have a 70 electrode, and its value comes out to be 111.35 kips, and it is basically the without the value of the phi, or I would say it is the nominal strength, not the design strength of the weld. Similarly, we will find out the thickness or the weld strength for 8 inches long weld which is loaded perpendicular to the weld, and it will become as 0.773 by 16 inches into 8 inches into zero point 0.6 into 70, and it comes out to be 44.54 kips. But you might be confused that why we didn't use the equation of the sine theta, that because the weld is applied perpendicular to the force. So in order, because this is not the design strength, the reason is this is not the design strength, this is the nominal strength that we have find out. If we find out the design strength, we will use the value of the time. So yes, no. If we move ahead, I will further tell in coming points or coming sentences. You will get the better idea of what I am talking about. Now, if we find out the design strength as per ASD manual, 14th edition, it says that nominal strength or the net nominal strength or total nominal strength comes out to be the Summation of the strength of all these welded, it comes out to be 155.89 kips. Similarly, if we use the equation J210B of AISC manual of 14th edition, it comes out to be nominal strength. It comes out to be 0.85 times the strength of the weld which is welded loaded along the weld plus 1.5 times which is times the strength of the weld which is loaded perpendicular to the weld, and it comes out to be 161.46 kips. Once we have these two values from the equation J210A and J210B of AISC manuals of 14th edition, then we will select the largest one for the design strength. And the 5, then we multiplied it with the 5, which is the value of 0.75, and design strength come out to be 121.10 kips. No, the point I'm talking about here that we did not use multiplied with the sine theta is actually catered here in the equation J210b, because if, as in the last question as we see that whenever the strength is loaded, member is loaded perpendicular to the weld, that is an angle of 90 degree, its value comes out to be 1.5, like here it has been stated, because sine 90 comes out to be 1 and 1 is added with the point 0.5, its total value comes out to be 1.5. That is why it has been taken into account into the equation of J210B of AISC manuals. But it doesn't matter if you multiply it here as well, it simply then add its value. You will going to get the same results as well. But if you multiply it here, you are not going to use this equation, in which we do not consider the weld and load orientations. That whether the load is applied perpendicular to the weld or parallel to the weld, they are simply just added up. While if we consider the weld and the load orientation, we use this equation which use the additional factor of safety as well. Now, let's move towards the calculations or the next problem of example 3, in which we are going to calculate the design strength based on the LRFD design theory, which is the load and resistance factor design method, for the same problem, for the same structure, or for the same connections that we used in the example 2, except that the thickness of their weld has been increased from 3 by 16 inches to 5 by 16 inches. Rest of the all the statements and the problems are the same parameter range. And the question demands that we have to find strength based on yielding of the cross section, and we have to find on the strength based on the tensile fracture of this member as well, or the shear capacity, and we have to find out the strength based on the block shear failure. That member can also be failed in the block shear that I have told you in the tension design of the tension members. Then we have to find out the weld strength, and then ultimately we have to decide that what will be the design strength for the entire connections, because in the connections there are two parameters are involved. One is itself the member in which it has been connected, and the second is the weld. Because if we have a failure in the weld, ultimately the connection is going to fail. If we have a failure in the member, again the connection is going to fail. So we have to find out the all parameters in the consideration, and then we will decide the what will we are going to have the total design strength of the sections. So, in the for the solutions for the first part, which is basically the yielding of the cross section, we will use the same formula for the yielding that we have used for the tension members, because the load applied here is in this form in the tensile direction to the member. It is basically pulling the member outward. So the load then value of the formulas used for the tension members will be used here. That is 5 times Pn is equal to 5 times Fy into Ag. And the value of phi for tension members is zero point 0.9, and the value of yield stress for A36 steel is 36 KSI, and the cross area of the member will be 8 inches, which is the width of the weld multiplied by the thickness of the weld, which is half inches. So it will come as 8 into zero point 0.5, and it comes out to be 129.6 tips. The next part is the strength based on the shear or the tensile fracture. We will use the formula of phi t Pn is equal to phi Fu into Ae, where Fu is the ultimate stress and its value for A36 steel is 58 KSI, and A is the effective net area. And as I told you in the classes, that effective net area is basically equals to U times AN, and where U is the factor of safety for the connections or for the block shear block. And if we will find the value of the shear U based on the type of the sections, and for this particular type section, if you move towards the table D 3.1, it comes out to be 1. And you can move on to table, you will see find out that its value is 1. But as moreover, I have also told you that whenever we have a welded fractions, its value is always equal to 1. However, for boards, its value can be 0.85, zero point 0.6, zero point 0.9, depending on the type of the section, whether we have a W section, S section, I section, C section, or whatever the other type of the structure we have. So for this particular problem, net effective area which comes out to be U, which value is 1 times the net area of the member, and its area of a member will become again 8 into zero point 0.5. So net effective area comes out to be 4 square inches. So if we plug in the values back into the formulas, so net for the shear or the tensile rupture, it comes out to be 0.75. The value of phi for shear, Fu 58 KSI for A36 steel, and AE we have found out that its value is 4 square inches. So it comes out to be 174 kips. Now the third strength that we have to find the strength based on the block shear failure. And for the block shear failure, the phi is, as the name indicates, it is block shear. Its value of the y will again be 0.75. And the equation for the block shear that we studied for the tensile members is Rn is equal to zero point 0.6 Fu into ANV. ANV indicates the net effective area in the vertical direction. And plus UBS is basically the factor for the tension stress, or the factor for the block shear tension stress, times Fu into A and T net. Total net area should be less than equal to zero point 0.6 times Fy AGV, that is gross vertical area, plus UBS FUA and T total net area. So for this particular problem, AGV, that is gross vertical area, it will becomes as 2 into 10 inches, because we have two weld of 10 inches, that we have a two weld, its length is 10 inches and the length is 8 inches. So we have a two weld, one on the upper side, one on the lower side. So it will come as 2 into 10 inches into thickness of the member of the plate, that is point half inches or zero point 0.7, zero point 0.5 inches. So it comes out to be 10 square inch. And in case of welded connections, net area is basically the equal to the gross area, so its AGV will be equal to the A and V, so it will come as 10 square inches. However, in the case of board connections, this net area will be lesser than the gross area because we have subtracted the value of the or the area of the board from the total area of the member. So ANT is the net transverse area, and it is basically the 8 inches multiplied by the thickness of the plate, that is half inches. So it comes out to be 4 square inches. UBS for this particular member comes out to be, again, its value is 1 because U is always taken as 1 for the welded connection. So we just have to plug in the welds back into the block and block shear equation. So it will come as Rn is equel to zero point 0.6 into Fu, which value is 58 ksi, plus Anv, its value comes out to be 10 square inches, plus Ups, its value is 1. Again, Fu is 58 ksi and Ant comes out to be 4 square inches. And it comes out to be 580 kips for first part of the equation. Hence, we apply the second part of the equations. It is Rn is equal to zero point 0.6 times Fy, which is 36 ksi. For a 3016, it was AGV, its value is 10 square inches, plus 1 into Fu, again 58 ksi, into A and T transverse areas comes out to be 4 square inches, and its value comes out to be, after simplification, is 448 kips. If we see the equation, it states that first part of the equation should be less than or equal to the second part of the equation, which means that we have to use the value of the that part, whichever value is the smaller, whether it is this first part of the equation or the second part of the equation. So basically, that will be the governing factor, or that will be the controlling factor for the block shear. And then we multiply it this the calculation of the design strength with 5. Then the 5 for shear is 0.75 into 448. It comes out with 336 kits. We will apply this formula for the design of the block shear. These are the strengths that we calculate for the members. First one, strength based on the yielding of the section. Second is the strength of the section based on the shear. Third is the strength of the section based on the block shear. And it is for the both the weld and the section. In the next part, we are going to find out the calculate the strength of the weld. And for the weld, we are going to follow the same procedure that we adopted in the example 2. That is, we have two 10-inch long welded, so we will multiply this 5 by, that is the thickness of the weld is 5 by 16 inches, multiplied with 2 into 10-inch long inch weld is into 0.6 into 70, and it found to be 185.6 kips. Then we will find out the strength of the weld which is loaded perpendicular to the weld, and it comes out to be 74.24 kips. Then we will apply separately equation, apply the two equations, that is J to 10A, without, which do not consider the weld orientation and load orientation, and it's just add up these two values, and it comes out to be 259.8 kips. While when we apply the equation J to 10B of AISC manual of 14th edition, its value comes out to be 269.1 kips. And we will select the values from these two equations, 10A and 10B, whichever is the largest. So our weld strength comes out to be 5Rn is equal to 0.75 into the largest value, and after simplification it comes out to be 201.8 kips. So we find out the strength of the weld as well, strength of the member, and tension, and shear, and the block shear. So our the controlling strength of this particular type of connections will be the one which is the smallest in all these criteria. For part A, its value of the strength is 129.6 kips. For part B, its value is 174 kips. For part C, its value is 336 kips. And for part D, its value comes out to be 201.8 kips. So it means that the controlling factor for this particular type of connection is the yielding of the cross sections, and its value is to 129.7, and which ultimately becomes the our design strength for this particular type of the connection as well. Because if our member fail in the tension at an angle of force of 129.6 kips, no doubt that member is not going to fail in shear or in block shear or in terms of the welding or in terms of the weld action shear. But if member fails in the tension, ultimately the our connection is again going to fail. Therefore, our design controlling criteria is based on the shear of the section, yielding of the section, block shear of the connection, and the weld strength. So whichever value is smaller, that ultimately becomes the design strength for that particular type of the connection. For this type, it comes out to be around 130 kips. That's all for today. I hope you will be able to design and analyze the welded connection in steel structures, irrespective of the type of the section and the length or thickness of the weld or the force applied on the weld. If you have any doubt, you are more than welcome to ask at any time. Thank you for today. Thank you for listening. Allah.